section 5.1.3, currents. A classic example of a moving charge is a current. Okay. The current has units of ampere, and that is the amount of charge traveling through some space per unit time. Coulombs per second is the unit of the amp. So if I imagine some wire or some line of charge, I can go ahead and define it having a charge density lambda, a line charge, and it's going to move along with the speed of v. Now, because the direction of that charge is determined by the shape of the wire, I should actually think about it as being moving along with some velocity down that wire. And I can define the current as the charge density times the speed, or times the velocity rather, and therefore the current is a vector. Okay. So if I have a wire that's carrying some current, and that wire sits in a magnetic field, that wire will feel a force. It will feel the magnetic force, which is given by this expression right here, which is just the differential, or the integral version of a previous video. All right, the velocity of that charge, the magnetic field that it sits in, and if you add up all of those charges, you would then get the total charge Q. Okay. All right, so I can go ahead and write that and break dq up into its components, v cross b. Now my infinitesimal chunk of current is really the charge density times some infinitesimal chunk of my path of my wire. Oh, this is not a vector yet. Okay. And I know that if I take the product of my velocity and my charge density along my wire, that is my current. So that's my current crossed with B dl. And this dl is a scalar right now, but dl always points along the path that my current is flowing, and therefore it always has the same direction as the current. So I can go ahead and think about this instead as being the vector quantity. I bring that into here. And if the current is constant in magnitude, I can take it outside of this integral, which it often is. Okay, so I can calculate the magnetic force that that a wire carrying a current that sits in a magnetic field feels. Now let's do an example. Example 5.3 says that there is a region of space where where there is a magnetic field, and all of the magnetic field points into the page. Okay, that's what this X represents. I think we've talked about this before. It's a uniform magnetic field, and there is a rectangular wire that sits partially inside of this field. This wire loop has a mass attached to it, and this wire loop has a current that's running through it. Okay, so it has dimensions. We'll say this dimension is A right here. And our goal is to figure out what is the current that is necessary for this to run through this loop so that this mass stays in one spot, right? So it doesn't fall. Okay. The only way for this to happen then is for you to think of having a free body diagram. You have a gravitational force, and the only way for it not to fall is for you to have an upwards force, and that can only come from this case, the magnetic field. Okay. So we need to figure out what that magnetic force is, and to do that we need to figure out what the current is. Okay. So our goal here, first we have to pick a direction for this current to flow. All right. In the end, what we're going to do is we're going to take cross products of the current and the magnetic fields. Okay. So we need to figure out a directionality associated with this. Okay. I'm going to start at the top of this loop and say that, all right, if my magnetic field is pointed into the page here, what direction must my current flow so that when I take the cross product of I and B, I get something that points up? All right, well, if I go ahead and pick a current that flows to the right, do the right-hand rule, hand goes in the direction of the arrow, curls into the page, and that gives me a force up. Okay. So I'm going to go ahead and say that's the correct orientation for the current, and that means that all the way along my loop, I have to go ahead and adjust so that the current flows continuously. Okay, I'm going to go ahead and integrate over this whole loop because I should. So I'll call this piece 1, 2, 3, and 4. Okay. So what I need to do is integrate over I dl cross B for 1, for 2, for 3, and for 4. Okay, so let's start with number 1, I guess. Let's start with an easier one. Okay, let's start with number 4. If I'm going to do this integral and I'm going to walk along the current direction dl, that means I'm going to walk along this arrow. Okay, but there's no B field anywhere along this stretch of the wire, so that's 0. Okay. Then let's do number 2. I'm going to walk along this wire. My B field is constant, so I can go ahead and say that this integral is going to go from some distance, or 0.1 to 0.2, whatever that is. I'll just draw that there, of dl cross B. Well, we can go ahead and write this dlb, and our direction is going to be up. This cross product is, this is the magnitude of dl, the magnitude of B, and the sine of the angle between them, just 90, and the direction is going to be up. Okay. So this becomes I, B, adding up all of the length of that bit of the wire. Well, we know that is a distance A. Okay. And this is still pointed up. Okay. Now let's go ahead and do 1 and 3 kind of at the same time. All right. If I were to walk somewhere along this piece of the wire, I would get a force that points this way. Likewise, if I go ahead and walk along some part of this wire, I do the right-hand rule, and I get a force this way. Those magnetic fields are the same, and therefore the forces are pointed in opposite directions but with equal magnitudes, and they all cancel out uniquely each one. Right, so there's for every force that it's felt on side 1, it cancels out with side 3. Okay. So therefore, the only surviving component that we have is this force IBA, and if this is going to be stationary mass that starts at rest, that means that these two forces must be equal to each other, IBA, and therefore the current that flows through this wire must be related to mg over AB. All right. And as you can probably guess, if you had a bigger mass, you probably would need to run a bigger current to hold that thing up.